Assalamualaikum warahmatullahi wabarakatuh. Today, our group from CDCS 110 will be presenting on the application of logic in real life. First, let me introduce our group members. First, Abdul Harith NAUFAL bin BADRULHISAM. Second, Muhammad SAIRULZIHAN ISLAHUDin. And finally, ZARIF RIDHWAN bin ZURAIMI. For this assignment, we chose topic 5 from our discrete math course, which focuses on the fundamentals of logic. Why did we choose this topic? Firstly, is because it forms the foundation of logical thinking used in mathematics and computer science. Next, helps understand how statements, connectives, and argument are constructed. Furthermore, it enables systematic reasoning to determine whether the conclusions are valid. Second last, applicable to real-life problems, especially decision-making and security-related scenarios. And finally, supports problem-solving by combining theory with practical application. Once we've chosen the topic, we need to understand what the fundamentals of logic are. Fundamentals of logic, also known as mathematical logic, is the branch of mathematics that studies formal system of reasoning by analyzing statements, their truth value, and the rules that govern valid inference. It provides a structured framework for constructing, evaluating, and proving the validity of argument using logical connectives, rules of inference, and truth tables. As you can see here, based on this mind map, essentially, logic consists of statements and logical connectives, truth tables, rules of inference, and finally, arguments. To understand logic, we start with statements and logical connectives. Think of connective as a glue that joins simple ideas together. We have negation, which you can say not, conjunction for and disjunction for or. We also use implication for if-then scenarios and biconditionals for if and only if. Once we have our statements, we use rules of inference to draw valid conclusion. The first one would be modus ponens. This is the most direct rule. Moving on, let's examine the more complex reasoning pattern. The first one will be modus tollens. If P leads to Q, but Q is proven false, then P must also be false. Next one, hypothetical syllogism. This works like a logical chain. If P leads to Q and Q leads to R, then P directly leads to R. And finally, if we are to given a choice between P or Q and we find out that P is false, then Q is the only remaining valid option. Next on the list would be addition. If P is already true, then the statement P or Q is automatically true because at least one part is satisfied. The next one is simplification. If we know both P and Q are true together, we can confidently conclude that P is true on its own. And finally, conjunction. If we have two separate true statements, P and Q, we can join them to form a single combined statement. Actually, there are many more rules of inference, but for our assignment, we have decided to focus on 4 main rules, which are modus ponens, modus tollens, disjunctive syllogism, as well as conjunction. After that, I'll explain truth table. What is truth table? A truth table is used to list all possible truth value of a logical expression. Truth tables helps determine whether a compound statement is a tautology, contradiction, or contingency. Truth tables are important tools for verifying the validity of logical arguments. Let's take a look at the example. As you can see, this is example of truth table. And finally, we will look into the arguments. What is argument? An argument consists of a set of premises followed by a conclusion. Their validity can be determined through the application of rules of inference and truth tables. A valid argument ensures that if all premises are true, then the conclusion must also be true. Let's look at the example. The valid argument for the first one using modus ponens. Premise 1, if it rains, then the ground is wet. As for premise 2, it is raining. Therefore, the conclusion would be the ground is wet. For an invalid argument example, affirming the consequent. Premise 1, if it rains, then the ground is wet. The second premise is, the ground is wet. The conclusion, therefore it rained. It becomes invalid because the ground could be wet from other sources. And finally, a valid argument using disjunctive syllogism. Premise 1, either P or Q is true. Premise 2, P is false. Therefore, the conclusion is Q is true. Next, I'll let Naufal continue on how to use fundamental of logic to solve real-life problems.
Now, I will present the next section, which focuses on the concepts and applications of logic in a real life situation. In this section, our group applies logical statements, rules of inference, and even truth tables to a cybersecurity case study involving students' online accounts and personal data protection. Okay, now let's take a look into our case study. As my friend SAIRULZIHAN has mentioned before, our case study focuses on cybersecurity measures and personal data protection, which means we consider situation related to cybersecurity issues. So, cybersecurity is the protection of computer systems, online accounts, and personal data from unauthorized access. In this case study, we conducted a simple observation and discussion among friends and found that many students use weak passwords and authenticate enabling two-factor authentication because they rather feel or find it inconvenient. As a result, some students experience account hacking where unauthorized users or hackers gain access and compromise their personal data. These situations led to questions about how strong passwords and two-factor authentication help prevent such incidents. Based on this scenario, logical statements were formed to represent the conditions of account vulnerability, hackers' access, and even data security. The principles of logical statements, rules of inference, and truth tables were then applied to analyze whether students' personal data is secured under these conditions and to determine the validity of the argument. Now, let's look at how this real-life cybersecurity situation can be expressed logically. We do this by stating all the conditions involved in the problem. So let's take a look. The first premise, either students use strong passwords or students' accounts are vulnerable. The next premise, students' accounts are not vulnerable. The next premise, students using strong passwords is a sufficient condition for students to enable two-factor authentication. The next premise, hackers gain unauthorized access only if students' accounts are vulnerable. The last premise, if students enable two-factor authentication and hackers do not gain unauthorized access, then students' personal data is secured. To simplify the situation, we define several logical variables. The first one, P, represents students use strong passwords. And then Q represents students' accounts are vulnerable. And then R represents hackers gain unauthorized access. And then T represents students enable two-factor authentication. And then the last one, S, represents students' personal data is secured. These variables allow us to translate the real-life situation into logical statements. Based on the case study, we form five premises. The first one, P or Q, or P disjunction Q. The argument is either students use strong passwords or students' accounts are vulnerable. The second premise is negation Q, which means students' accounts are not vulnerable. The third premise is P implies T, which means students using strong passwords is a sufficient condition for students to enable two-factor authentication. The fourth premise is R implies Q, which means hackers gain unauthorized access only if students' accounts are vulnerable. The last premise is T and or conjunction negation R implies S, which means if students enable two-factor authentication and hackers do not gain unauthorized access, then students' personal data is secured. All these premises are then combined into one logical expression, as you can see here. And then this expression shows that if all the premises are true, then the conclusion S must also be true. So how do we solve this logical expression? How do we prove that the conclusion is indeed S? And how do we prove or determine all the arguments are valid? So let's solve it together. So as we know, we have five premises. Okay, premise 1, 2, 3, and 4, and 5, as you can see it here. And then what is the next step? What should we do? So for step number 6, what we're going to do is we would take premise number 1, which is P, or we call this disjunction Q, and then we take premise number 2, which is negation Q. Okay, and we apply disjunctive syllogism on them, which is one of the law of inference. So when we apply disjunctive syllogism on these two premises, we would get P. Okay, P is the result from applying these rules. Okay, so what is the next step? When we already get P, and then we can move on to the next step. Now we would take premise number 3, which is P implies T, and then we take premise number 6, which is P. Okay, when obviously when we have these two kind of premises, one is a conditional premise, and then the other one is just a standalone variable, or just a one premise. What you could do is you could apply modus ponens on them. So what we would get at the end is we would get T. Okay. If you notice the pattern here, if we apply modus ponens on, when there's same variable, we would just ignore it and take the one that contradicts or different from it. So we would get T. Okay, we will get T. So next, what we're gonna do, okay, the next step is we're gonna take premise number 2 and 4. Okay, what is premise number 2? Premise number 2 is negation Q. Premise number 4 is R implies Q. Okay, when we have these premises, we could apply modus tollens. Okay, because why? Because we have Q and negation Q, and then the result we will get negation R. Yeah, as you can see it here, it's negation R. Okay, after that, okay, when we already have negation R, the next step is we're gonna take premise 7, which is T, okay, premise 7, and then premise 8, which is what we already got before, negation R. And what we could apply is we apply the rules of conjunction. In loss on inference, when we have uh, two standalone variables or premises, what we could do is we combine them together by using loss on inference conjunction. So we just combine them. T conjunction negation R. Okay, and then we have the answer for step number 9. Okay, we have this new premise. So the last one, how do we get conclusion S, is that we're gonna take premise 5 and 9, which is this T and negation R, okay, and implies S. Okay, and we take premise 9, which we already got before. Okay, notice that we have the same thing over here. Okay, same thing on these two premises. What we can do is we apply modus ponens. Okay, we apply modus ponens, and then we would get result S, and we will get the conclusion that we want or we expected. Okay, so conclusion is S, which means students' personal data is secured. Now let's take a look at truth table. To further support our argument, we use the truth table for the entire logical expression. The truth table lists all possible truth values for the variables p, q, r, t, and s, and evaluates the expression under every possible condition. To construct the truth table, we list all possible truth values for the variables p, q, r, t, and s. Then, we evaluate each component of the logical expression step by step, starting from the simplest statements and building up to the complete expression. The purpose of constructing this truth table is not to analyze every row individually, but to verify whether the final logical statement is always true. So instead of explaining the truth table row by row, we focus on the final column. The final column represents the value of the whole statement, the whole logical expression, as you can see there. Based on the constructed truth table, the final column shows that all the true values are true, which indicates that the logical statement is a tautology. Since a tautology is true under all possible conditions, the argument is considered valid. This supports the rules of inference used earlier because the truth table confirms that there is no case where all the premises are true and the conclusion is false. Therefore, the truth table strengthens the validity of the argument by verifying the inference result under all possible true values. Now, let's move on to the next part.
In conclusion, this presentation demonstrates how the principles of logic can be effectively applied to real-world problems, particularly in cybersecurity and personal data protection. By using logical statements, connectives, rule of inference, and truth tables, the validity of the arguments was systematically evaluated. These results show that the argument is a tautology, which confirms the conclusion stating that students' personal data is secure, is logically valid. This highlights the importance of logical reasoning in making accurate decisions and solving real-life problems structured manner. We have decided to include the suggestion for improvement. The first one is include complex scenarios. Future studies could include more complex scenarios involving additional variables to reflect real-world cybersecurity conditions more accurately. The second one is add more practice questions. More practice questions and examples could be included to strengthen understanding and improve confidence in applying rules of inference and constructing truth tables. There are also points to be careful about when using fundamental of logic to solve problems. The first one is rules of inference accuracy. When applying rules of inference, it is important to ensure that each rule is used correctly and based strictly on valid premises, as a small mistake can lead to an invalid conclusion. The second one is truth table prediction. In constructing truth tables, careful attention must be given to every possible combination of true value to avoid error that may affect the final evaluation of validity. That's all from us. Thank you for listening.